Hello, Design of Concrete Structures 1 students, CE703. I am Professor A.F.M. Abdurrauf. I will be dealing with the subject that is the design of design of a doubly reinforced beam. Today we will discuss design of a doubly reinforced beam. Doubly reinforced beam means there will be reinforcement at the bottom and at the top of the beam. Normally we use singly reinforced beam and we use steel in one layer, that means where the tension is there. But here in doubly reinforced beam, the steel will be used just for the tension zone and also for the compression zone. Because of that, the section will be limited, and for limiting the section, the compression will not be the concrete will not be able to take care of the full compression of the beam. That's why we will use some steel in the compression zone also for taking care of the excess compression. Now we will introduce a problem here, and the problem first of all will give the loads and span of the problem and the material properties, etc. And it is written in this text that we have to use a live load of 2.47 kips per feet and a dead load of 1.05 kip per feet, and the span of the beam is 18 feet. It's written here, and the beam section is 10 by 20. Beam section width is 10 and depth is 20 inch. Total depth. And Fy will be using Fy 60,000 psi and F prime C as 4,000 psi. And now we will go for the solution. First of all, we have to find out the factor load. The dead load factor for dead load is 1.2 and factor for live load is 1.6. So if we multiply the dead load 1.05 by 1.2 and 1.6 is multiplied with the live load, that is 2.47, and total is 5.21 kips per feet. Now we have to find out the moment at the maximum point is center, and normally uniformly distributed load is the uniformly distributed load, and the moment will be WL square by 8, and W here is 5.21 and L is 18 feet and 8 is 8. That's why the moment is 211 feet kips, and that if we keep it in inch kip, then we have to multiply it by 211 by 12, and that becomes 2530. And now the overall section is given as 10 by 20, but effective depth of this section we have to first of all calculate the effective depth, and for calculating the effective depth, normally if you put one layer rod at the bottom, then we deduct 2.5 inch, and if we place 2 layers of rod, then we have to deduct about 4 inch from the total depth. That's why the effective depth will be, in this case, the effective depth after deducting 4 inch, the effective depth will be 18 inch. The effective depth will be 16 inch. And there is another term is D prime. D prime is the term which is where this negative steel or the compression zone steel is placed. From the center of the compression zone steel, the outside of the beam, there must be some dimensions for clear cover, stirrup, and the rod placing. That amount is normally kept as 2.5. Like in beam, for one layer of rod, we have to keep from center of the rod to the outside of the beam 2.5 inch. That's why D prime here is 2.5 inch, and effective D is 16 inch, D prime is 2.5 inch. Is that clear? Now we will first of all find out the rho value, and the rho value of this beam will be, as we have all data, and we know the rho equation is rho 005 means we will take the strain of steel as 005, and for concrete strain is always 0.003. That's why the general equation for rho, as we have discussed it in earlier classes, then you know that rho is, the equation is 0.85 beta 1 f prime c divided by fy, epsilon u divided by epsilon u plus 0.005, etc. And if we put the value of f prime c and fy as 4 and 60, and epsilon u as 003, and epsilon 005 is epsilon 005, then the value of rho is 0.0181. Now, then AS will be for this section, as the rho is 0.0181, and steel area will be rho BD. B is 10 inches and D is 16 inches. We have discussed this in previous pages, and the AS required is AS coming as 2.90 inch. And from this A, and from this steel area, we can find out the A value for this steel area of 2.9 for the general rho of 0.081. With multiplying the cross section, effective cross section, we get 2.9 as this 9 inch square as the steel area. And if we know the steel area, we can find out the stress block depth. Rectangular stress block depth, the depth is A, and the depth value here is AS still into A. This is the formula for finding out A, ASFY 0.85 F prime C into B. If we put the numerical values of AS and FY and F prime C and B, that becomes 2.9 into 60 divided by 0.85 into 4 into 10 is equal to 5.1 inch. If we know there is a relation between A and C, and if we know A, then we can find out value of C. We will require this value of C, compression block depth. The value of C will be alpha divided by beta 1, A divided by beta 1. Here A is 0.512 and beta 1 is for this concrete 4000 psi concrete, beta 1 is 0.85. That's why the C value, the neutral axis depth of this beam is 6.02 inch. Neutral axis depth of the beam comes from small c is the symbol of neutral axis depth for beam, and here alpha A is the A value is calculated in the previous line, and beta 1 is for 4000 psi is 0.85. You can get it from the earlier lecture, beta 1 value, and here we have used that value from that chart, and the C value is 6.02. C is the neutral axis depth. C is the neutral axis depth for in the beam. There are some symbols, those are standard symbols like D, B, small c. All these are known to you, that the small c is the neutral axis depth, and this value is 6.02, and the maximum nominal moment that can be developed as singly reinforced beam is equal to Mn is equal to AS Fy D minus A by 2. This is the formula for finding out moment from steel area and Fy. If you know these values A, etc., you can see in the previous lectures or in the text that this sort of equations are there available, and we will use that equation. And here our AS is 2.9 and Fy is 60 and D is 16, and A, just we have found out A in the previous line, that is 5.212, and A by 2 is 5.12 divided by 2, and this gives us the moment carrying capacity of this section is 23,440 inch gives. Corresponding design moment is, if we multiply this by the reduction factor, moment reduction factor, then which is 0.9, then we have used 0.9 and multiplied this with the moment, the nominal moment, and then we have got the ultimate design moment is 2100 inch skips, 2100 inch skips in this, less than the required capacity of 2530 inch skips. Previously we have calculated the total moment as 2530, but this section is capable of taking 2340 as the moment. That's why the remaining moment should be should have some treatment with steel at top and bottom. This excess moment must have some, to take care of this excess moment, we must provide some steel at the top and some steel at the bottom of the rod. That will make a couple and make this moment balanced. Then now with 2530 moment, we have to divide it by the 5 factor 0.9, and if we, after dividing 2530 divided by 0.9 minus 2340 is equal to 470 inch skips. This, for this moment, 470 inch skip, we have to provide steel at the top and steel at the bottom, and we will next go for the calculation how to tackle or how to take care of this 470 inch skip of excess moment by providing steel at the compression zone and steel at the tension zone. Next page. Here's a figure where we have given the details of the beam cross section and strain diagram. As you know that stress strain, in a strain diagram, a strain is in a straight line. At the top is the compression strain epsilon u. Concrete strain is denoted by epsilon u, and steel strain is denoted by epsilon s. We have shown on the right hand side of the figure, we have shown this strain diagram. In the strain diagram, you see that, and we have shown also the neutral axis depth. Previously, we have calculated this neutral axis depth of this beam as 6.02 inch, and that is being shown here with arrows. And we will provide the steel at the compression zone at a depth of 2.5 feet from the top surface, and that 2.5 feet is shown. And along the dotted line below 2.5 inch mark, the steel will be placed there. We have not shown the steel in the strain diagram, but we have shown the steel in the left hand side cross section. That's why the steel will be at 2.5 inch from the top of the beam, and the neutral axis depth is 6.02, and at the top epsilon u is at the failure condition or the design condition, the epsilon u is 0.003. Epsilon u is 0.003. We take it as 0.003 for all sort of concrete, all strength of concrete. And from this 0.003 and the neutral axis depth of 6.02, we can find out epsilon u is 0.003. We can find out epsilon s prime. We can find out epsilon s prime from the triangle properties. This triangle is a depth of 6.02 and width of epsilon u. Epsilon u value is 0.003. It is not written in the figure, but we know it is 0.00. Epsilon u is always 0.003. Therefore, at a depth of 2.5 from the top of the beam, epsilon s prime, we need the value of epsilon s prime, which is from this triangle properties, as we have shown here. 0.003 is multiplied by a figure, that is 6.02 is the neutral axis minus the 2.5 is the clear cover for the steel, and again at the bottom this is C value 6.02, and this gives us a value of 0.00175. And we know the modulus of elasticity of steel is 29 into 10 to the power 3 KSI, and if you know that you know that this value is in inch is 29 into 10 to the power 6 psi, but in kip this is 29 into 3 ksi. Here we have put 29 into 10 to the power 3 ksi value, and if we multiply the strain with the modulus of elasticity value, then we find out the stress. There is a relation between these two factors. Therefore, in this case we have found we have multiplied this 0.00175, which is the strain, and 29 into 10 to the power 3 or 29,000 ksi is the modulus of elasticity value. Then the stress at this position of the beam will be 50.9 ksi. That means when the beam will be at the failure condition, the stress in the steel at the compression zone will reach only 50.9 ksi, no more, no less. So the compression steel requirement will be calculated from this allowable stress of 50.9 ksi, and this the top rod is designated as AS prime, and the moment for which we need this extra steel at the compression zone is 470, and we have to divide this by 50.6 is the 50.6 I'm sorry 50.9 is the allowable stress, and 16 minus 2.5 is the distance moment arm. 16 is the effective depth, and 2.5 is the clear cover at the top. That's why the moment arm from between the rod at the top and rod at the bottom is the moment arm is 16 minus 2.5, and this gives us a value of 0.684 inches square. This is AS prime. That means in the compression zone we have to place we have to put this much of area, 0.684. This area we will convert into the number of rods depending on the diameter of the rod and the rod area, and now we have to calculate the steel for the bottom zone, tension zone also. In the tension zone, the allowable stress will be 60. That's why the steel required here will be less, and we can find out this by proportioning the allowable stress at the top and allowable stress at the bottom. But with the allowable stress 50.9, the value is steel area value is 6.684. If we proportion it by 50.9 by 60, then the steel area at the bottom, because the steel at the bottom will be stressed more, then the area required will be less. That's it. The area coming here is from the division, from the calculation, the area is coming here as 0.59 inches square. That's why the tension zone or the bottom of this beam, particularly this beam, the area of steel required will be 0.59. In the top, we use 0.684, and in the bottom, previously we have calculated a value for the moment as a singly reinforced beam. As a singly reinforced beam, we have calculated the area of steel at the bottom is 2.9, and now for this extra moment, the steel area is 0.59 for the bottom zone, and the total is 3.49 inches square. And this is in short is the method by which we can calculate the steel area for the compression zone and tension zone. That means we can design a doubly reinforced beam. Now we will just show the placement of the steel, number of bar, etc. in the next page. In the previous problem, we have listed a bar diameter and area. You can see that one, or you can memorize most of these bar areas, because you will be using many times in your life. Though presently the market bars are deformed, but in the textbook where we are using mainly the textbook of Nielsen, here they have used these round bars. That's why to keep with pace with the author, we are also using this round bars here, but uh, in practice we can have some equivalent round bars in the market and we can use that. Now we will be, for this problem solution, we will be using round bars, and the table I have given previously in the previous problem, we will refer that page, that table, and we will use the area. And here in the top we require steel area of at the top we need a steel area of 0.684 inches square, and if we provide number 6 bar, then that 2 bar will cover this much of area. If we want to use a smaller bar, that will not be sufficient, though it looks that the area of the number 6 bar is much little more than the area calculated, though we don't have any other alternative but to use number 6 bars at the top. Therefore, we will use number 6 bar at the top, though there will be some steel area excess. Doesn't matter, because we will, in most of the cases, we will not be able to get bars exactly according to the calculated area, because the bars are the bars are not there is a limited number of bars. The sizes cannot be made very fractional, something like that. That's why either we have to jump from one to another to some distance. That's why this number 6 bars is justified, though we will never be able to exactly use the size of the bar, because in that case the size of the bar or the diameter bar of the bar will become fractional. So number 6 bar at the compression zone will be a little bit more than the required one, but this is okay. And for the bottom, we have to use number 9 bar. Number 9 bar has 1 inch square area, and the required area of the bottom bar is 3.49. Here also we will not be able to find out exactly the amount by combination of several size of bars. That's why we will use single size of bar, that is number 4 bar will give you number 9 bar will give you 4 square inches, though it seems very little bit higher, then we will never use less steel, but if we keep it a higher amount for arranging the bars or choosing the number of bars or choosing the size of the bar, we have to use it, and this sort of uneconomy is allowable for the practical purpose. And so for this problem, here is the end of this one, and we will see this figure here. In the figure, as previous case, in the previous problem and previous discussions, we have said that if there is single layer rod, that the center of that bar in the beam should be 2.5 inch from the center to the outside. And in the bottom bar, there are 2 layers. There must be a clear cover. Here, the required is 2.5 inch, but for arranging, for calculating, here we have shown a round figure of 2.3/4 inch instead of, no, bottom bar should have been at standard is 2.5, but we have used for making round figures, etc. We have used 2.3/4 inch, and from this bottom rod to the top rod, we have to keep a gap of 2.5 inches, and this is shown here. And in your life, you have to also show this sort of gaps and arrange the steel area like that. And in between these 2 layers of rod, there must be a spacer rod, which should not be less than 1 inch, or in most of the cases, it may be the bar size, which is available easily. That's why, though here it is from center to center, it is 2.5 inch, but the rod two rod, half of this 2 rod diameter will be 1 rod, and the space will be the space for the spacer, and this space between the bar is required for passing the aggregates in between the bars while you will be casting this beam. And if there is not sufficient gap between the bar layers, then the coarse aggregate will not pass in between these two layers, and only the slurry will go there, and the concrete will not be a strong concrete, and the strength of the concrete will not come to the up to the standards. That's why you must keep this spacer bar at least minimum the size of the main bar or 1 inch, whichever is more. If the bar size is more, then we have to keep that size of space, and if the bar size is smaller, we have to keep at least 1 inch or the 1/3 of the maximum size of the coarse aggregate. And these are the requirements for bar placing or bar arrangement. And I hope you will be able to understand it and try to follow thoroughly, and hope, though this is a little bit a tough problem, if we repeat, if you go once or twice or thrice, then you will be able to understand the problem fully. Just seeing it, you will not understand. Try to understand line by line, step by step. If there is any problem, you discuss yourself with other fellows, and so we are through this problem. Hope you will be able to. We have discussed doubly reinforced beam. This is a little tough problem, and you have to be very sincere, and you will try to understand it. And if you do not understand by reading once or twice, you have to discuss with your classmates or with us, and the point where you have the difficulty. For this course, this doubly reinforced beam is a little tough problem, so you must give emphasis in learning this, and this is a popular question also in the examination or anywhere, doubly reinforced beam, and we will frequently face doubly reinforced beam design, because wherever the section restriction is there, we have to use doubly reinforced beam. Section restriction is most of the time will come up in the buildings where we want to keep the building height at a minimum for different reasons. That's why the doubly reinforced beam will be coming in any building, anywhere, anytime. So you have to learn this one and understand it, and try to be clear about every point of it.